Somewhere inside a government research lab in California, scientists just quietly broke a piece of technology that has not fundamentally changed in almost 200 years. Not a new paint color for your kitchen appliance. Not a slightly more efficient compressor. An entirely different way of making things cold, one that does not use the gas-based refrigeration cycle every single refrigerator, air conditioner, and freezer on the planet has depended on since the 1830s. This is not a concept sketched on a whiteboard. It has already been built, tested, and published in one of the most respected scientific journals in the world. We are talking about a cooling method that uses no compressor, no refrigerant gas, and none of the environmentally damaging chemicals that have quietly been warming the planet every time your fridge cycles on. If you like videos like this, please hit the like button, because these take a lot of work to put together, and subscribe so you do not miss the next one. What this invention does is not a small tweak to an old idea. It is a genuine replacement for the basic physics. Every cooling appliance on Earth has relied on for 2 centuries, and understanding how it works means understanding why the refrigerator you are standing next to right now might not exist in its current form much longer. A different way to make cold. The technology at the center of this story comes out of Lawrence Berkeley National Laboratory, a facility run by the United States Department of Energy, and it goes by the name ionocaloric cooling. Researchers there built a method of moving heat from one place to another using charged particles called ions instead of the pressurized refrigerant gas that every conventional fridge and air conditioner depends on. The breakthrough was significant enough that it was published in the journal Science, one of the most competitive and closely scrutinized scientific publications on Earth, meaning the claims behind it have already survived intense scrutiny from other scientists before ever reaching the public. Every refrigerator currently sitting in a kitchen anywhere in the world works the same basic way. A compressor squeezes a refrigerant gas, forcing it to heat up, then lets it expand and cool rapidly. And that expanding, cooling gas is what pulls heat out of your food compartment and dumps it into the room behind the appliance. This is called vapor compression refrigeration, and it has been the standard method of artificial cooling since the 1830s, refined over time but never fundamentally replaced. The ionocaloric method throws that entire mechanical process out and replaces it with something closer to chemistry than mechanics. Instead of compressing gas, this new system relies on a phase change, the same basic physics behind ice melting into water or water boiling into steam, except deliberately controlled and triggered using electricity. And the way researchers trigger that phase change is where the real cleverness of this invention becomes obvious, because they borrowed the idea from something most people have seen happen right outside their own front door in the middle of winter. The salt trick scaled up to laboratory precision. Anyone who has watched a road crew spread salt before a winter storm has already seen the basic principle behind this invention in action, even without realizing it. Pure water freezes at 0 degrees Celsius, but add salt to that water, and the freezing point drops, sometimes dramatically, which is exactly why salted roads stay wet and slushy, instead of turning into solid ice during a storm that would otherwise freeze plain water solid. The salt is not making the road warmer. It is changing the temperature at which the water on that road is willing to change from liquid to solid in the first place. Berkeley lab researchers took that same basic idea and turned it into a precisely controlled cooling engine. Instead of ordinary table salt dissolved in water, their system uses a sodium iodine-based salt combined with a solvent called ethylene carbonate, a material already familiar to battery manufacturers since it is commonly used inside lithium-ion batteries. By running a small, carefully controlled electrical current through this mixture, the researchers can push ions through the material and shift its melting point on command, essentially flipping the material between solid and liquid states whenever they choose, rather than waiting for the surrounding temperature to naturally cross that threshold. Here is why that matters so much. Every time a material melts, it absorbs a burst of heat from its immediate surroundings in order to make that transition from solid to liquid. And every time that same material freezes back into a solid, it releases that same burst of heat back out. That absorb and release cycle is precisely what a refrigerator needs to do. Pull heat out of your food compartment during one part of the cycle, then dump that heat elsewhere during the other part. The Berkeley team essentially built a system that can trigger melting and freezing on command using nothing but a small electrical current, using that repeated phase change as the engine for moving heat, instead of a mechanical compressor squeezing gas back and forth. Think of it like a light switch, controlling not electricity, but the temperature at which a specific material decides to freeze or melt. Flip the ion current one direction, and the material's melting point shifts low enough that it turns to liquid, soaking up heat from its surroundings as it does. Flip the current the other direction, and the melting point shifts back up, causing the material to refreeze and release that stored heat somewhere else. No compressor. No moving mechanical parts grinding against each other. No refrigerant gas sealed inside pressurized tubing waiting to leak. Why this could matter more than it sounds? The obvious question is, why replacing a compressor with an electrical ion trick actually matters in the real world? And the answer comes down to two problems that have quietly plagued cooling technology for decades: energy efficiency and environmental damage. Traditional vapor compression refrigeration is fundamentally wasteful. Every time that compressor runs, mechanical friction generates wasted heat. Moving parts wear down over years of use, and a significant amount of the electricity going into your refrigerator is lost simply running the compressor motor itself, rather than directly moving heat where you want it to go. Ionocaloric cooling sidesteps almost the entire mechanical process. There is no compressor grinding away, which means dramatically fewer moving parts to wear out, break down, or need replacing over the lifespan of the appliance. Early published results from the Berkeley team suggest the approach has the potential to be significantly more energy efficient than traditional compressor-based systems, since the process directly harnesses a phase change instead of losing energy to mechanical friction and pressure cycling along the way. The environmental piece is arguably even more significant. Refrigerants used inside traditional compressor-based systems, the chemicals actually being compressed and expanded to create cooling, are frequently powerful greenhouse gases, some of them trapping far more heat in the atmosphere per molecule than carbon dioxide does. When a refrigerator, air conditioner, or industrial cooling system leaks, which happens more often than most people realize over the lifespan of an appliance, those chemicals escape directly into the atmosphere. Multiply that leakage across every refrigerator, every air conditioning unit, and every commercial cooling system currently operating worldwide, and refrigerant leaks quietly become one of the more significant overlooked contributors to global warming, entirely separate from the electricity those systems consume. Ionocaloric cooling eliminates that entire category of environmental risk simply by not using pressurized refrigerant gas at all. The materials involved, a specific salt dissolved in a solvent already used safely inside consumer batteries, do not carry the same greenhouse impact if they were to leak or degrade over time. For an industry that has spent decades searching for a refrigerant that is simultaneously effective, affordable, and environmentally safe, removing the refrigerant question entirely is a fundamentally different kind of solution than simply switching to a slightly less harmful gas. Why nobody solved this problem sooner? It is worth asking. Why, if this idea sounds almost simple once explained, using a version of the same physics behind road salt, nobody managed to build a working cooling appliance out of it before now? The honest answer is that moving from a neat scientific principle to a controllable, efficient, reliable engine capable of actually cooling something on demand is an enormous engineering leap, one that requires precise control over exactly how much electrical current to apply, exactly how quickly the phase change happens, and exactly how to manage that cycle repeatedly, thousands of times, without the underlying materials degrading. Scientists have understood that salt changes the freezing point of water for a very long time. That principle is centuries old, chemistry taught in basic classrooms. But turning that principle into a controllable cooling cycle using electrically driven ions in a system compact and efficient enough to potentially fit inside a household appliance someday required advances in material science and battery-adjacent chemistry that simply were not available until relatively recently. The ethylene carbonate solvent used in this system, for example, only became a well-understood, mass-producible material because of the explosive growth of the lithium-ion battery industry over the past 2 decades. An industry that did not meaningfully exist in its current form when engineers first started dreaming about alternatives to compressor-based cooling. In a sense, this invention is a direct byproduct of the battery revolution that has already transformed electric vehicles and consumer electronics. The same chemistry refined to make batteries safer, more energy-dense, and cheaper to manufacture. At scale turned out to be exactly the missing ingredient needed to finally make an old, mostly forgotten cooling principle into something that could work as a real, controllable engine rather than just a classroom demonstration. What still has to happen before this shows up in your kitchen? It would be misleading to suggest that a fully finished, ready-to-buy refrigerator using this technology is sitting on a factory floor somewhere waiting to ship. This research represents an early but genuinely significant proof of concept, published and peer-reviewed, but still a long way from the kind of large-scale manufacturing and long-term reliability testing that any appliance destined for millions of households needs to survive. Refrigerators are expected to run continuously for a decade or more without meaningful failure, cycling on and off thousands upon thousands of times, and any new cooling technology has to prove it can handle that same brutal, repetitive workload before manufacturers will seriously consider retooling factories to build it at scale. There are also open questions around cost. Scaling any laboratory chemistry process up to mass production typically uncovers challenges that never appear at a small research scale. Sourcing raw materials cheaply and reliably, engineering the system to be manufactured cheaply enough to compete with an extremely mature, extremely optimized compressor-based industry that has had almost 2 centuries to bring costs down. Compressor technology is not primitive simply because it is old. It is old because generations of engineers have relentlessly refined it into something remarkably cheap, reliable, and efficient within the physical limits of its basic design. Beating that kind of deeply optimized incumbent technology requires more than just a clever new principle. It requires years of further engineering to prove the new approach can be built cheaply and reliably at the same massive scale. Why this invention matters even before it reaches a store shelf. Even with those limitations acknowledged, the significance of this research goes well beyond a single lab result. For decades, the cooling industry worldwide has been stuck making incremental improvements to fundamentally the same idea: better refrigerant chemicals with slightly less environmental impact, slightly more efficient compressor motors, better insulation around the appliance itself. Nobody had seriously threatened to replace the basic vapor compression cycle at the heart of the entire industry, because nothing else had proven itself as a credible, scalable alternative. Ionocaloric cooling is the first approach in a long time that offers a genuinely different physical mechanism for artificial cooling, one that specifically attacks both of the vapor compression cycle's biggest long-term weaknesses: wasted mechanical energy and environmentally damaging refrigerant leaks at the same time. Even if this exact chemistry never makes it into a mass-market refrigerator, the underlying breakthrough using electrically controlled ions to trigger a precise phase change on demand opens an entirely new research direction that other labs and companies around the world are now almost certainly going to explore and build upon. There is also a quieter, longer-term implication worth considering. Cooling technology is not just about refrigerators sitting in kitchens. Air conditioning, industrial refrigeration for food supply chains, cooling systems for massive data centers and server farms that already consume staggering amounts of electricity worldwide. All of these systems currently depend on some version of the same basic compressor technology. A genuinely more efficient, environmentally cleaner alternative, if it can eventually be scaled and manufactured affordably, would not just change what sits in your kitchen. It could meaningfully reduce the electricity and environmental burden of one of the largest, most invisible energy demands in the modern world, one most people never think about until their power bill arrives in the middle of a heat wave. The refrigerator sitting in your kitchen right now is running on physics discovered before the American Civil War, refined constantly over 2 centuries, but never fundamentally replaced. For the first time in a very long while, a credible, published, peer-reviewed alternative exists, born not from a giant appliance company trying to sell you a slightly better fridge, but from a national laboratory chasing a completely different question about how heat and cold actually move. If this story about the invention that could make your refrigerator obsolete surprised you, hit the like button, subscribe, and turn on notifications so you never miss the next one. There are more videos on the screen right now if you want to keep exploring. So here is my question for you. If a refrigerator using this new cooling method hits stores tomorrow at the same price as what you already own, would you switch? Or do you want to see a few more years of real-world testing first? Let me know in the comments below.